Awesome. Thank you, Leila, for the introduction. I think Bryan has some introductory words before I'm going to start.
Hi, I'm just going to say a few quick things since Julie's going to do the whole presentation. But anyways, I just wanted to say to everyone, I'm excited to watch Dr. Mai wow you with all of her presentation results and all of our model intercomparison work. While this was certainly a team effort, this only happened because of Julie's passion and dedication and hard work to generate the best science possible. This project started, I don't know, 5 years ago, maybe when I wrote a few sentences for the IMPC proposal. So we didn't have an idea of how it might work, although I thought, we could probably, with the right person leading it, do a world-class intercomparison study. And Julie was that person. And Julie took over as soon as we got the funding, and she's led this project ever since. I'm really proud of this work. I feel like it's transformative. I'm proud of the team. I'm proud of Hong Ren, who's my student who helped out as a co-author, and particularly proud of Julie. I really think this work is transformative. It's certainly transforming how I'm doing science and research going forward. So hopefully it changes the way some other people do it too. So anyways, with all that, I'll pass it over to Julie. Thanks.
Awesome. Thank you, Bryan. So as Bryan already said, I am super excited to talk about this project today, the Great Lakes Runoff Intercomparison Project, phase 4, actually, over the entire Great Lakes. And this work wouldn't have been possible without all the amazing people contributing to it. They are all listed on this slide. They will show up later again, what they contributed. There's people from Canada, obviously, a lot of places in the US, but also some people from Europe joined in to help out here with some of the models they had set up. Before I start with the presentation, I want to start by acknowledging that we are participating today from the traditional territories of the first people across the country. Here in Kitchener-Waterloo, I acknowledge that I'm on the Haldimand Tract, land that was promised to the Haudenosaunee of the Six Nations of the Grand River. The Haldimand Tract is with the traditional territory of the neutral Anishinaabe and Haudenosaunee people. I would encourage you to take a moment to recognize the traditional land where you are on. I also would like to acknowledge the funding we received for this project. Hong Ren was funded through the IMPC, and myself, I was funded through the core modeling team here in Waterloo. So, as I said, the project I'm presenting here, GRIP-GL in short, is actually phase 4 of the GRIP project. It all started in 2014 and probably a little bit earlier with Lauren Fry, who did a model intercomparison with a lot of other people over the Lake Michigan watershed. After that, they moved on more or less the same group, but then led by Etienne Gabory over the Lake Ontario watershed. And then in 2018-19, I got that 5-liner Bryan was referring to for a model intercomparison over Lake Erie. So we started there and published that in 2021. And shortly before we had it actually finally published, we already had started with GRIP-GL, where we decided most people from the GRIP-E moved over with us to GRIP-GL. And we decided just to do the entire watershed instead of moving on to Lake Superior or Lake Huron or something like that, just doing the entire watershed and using all the knowledge project management wise as well from GRIP-E and transferred it into GRIP-GL. So that's what I'm going to present today. So what we ended up with in GRIP-GL is in total 13 different models. One of them is data-driven. It's an LSTM that you might have heard of before already. 12 are more traditional, like let's say hydrologic land surface model, probably most of the people are familiar with. But you can also group those models in a different aspect. 6 of them are lumped. They are just like aggregated for each watershed, each basin, and 7 of them are semi-distributed. Whatever that means, might be gridded or subbasins, it's semi-distributed. But then also like these models differ in how they are calibrated. There are 7 models that do a local calibration. So you give them a watershed and they calibrate for exactly that stream flow. They don't know that there's other basins around. It's exactly for that one basin. Then we have 5 models that are regionally calibrated, which in our case means it's just a larger unit. It's the entire Lake Erie watershed, for example, or the entire Lake Huron watershed is calibrated. So in our case, we ended up with 6 regions over the Great Lakes, 5 for the lakes and 1 for the Ottawa River. So the models have several final setups, but not as many as the local ones. And then there's one model that actually has a global setup. So a global Great Lakes setup, one model setup, and that is happening to be the data-driven model. The data-driven model is for the entire region. So we have a wide variety of models. That's what I wanted to say here. What all these models have in common is that they had to use the exact same forcing data set. There was no other additional information allowed to be used for any of those models, besides the about 10 by 10 kilometer square resolved RDRS data set. That's an 18-year data set. We skipped the first year for warm-up, then we use part of the data for calibration and part of the data for validation. Everybody also had to use exactly the same geophysical data. And that's a key point here, because in GRIP-E, everybody could just use whatever they wanted. So everybody used a different soil database because we couldn't agree on something. So in GRIP-GL, the very first meeting we ever had was, this is the variety of soil databases we use in GRIP-E. Why can't we pick one of them? And it was actually pretty straightforward at that point to agree. It took us 30 minutes to agree on the common data set, which was impossible to agree on when we started GRIP-E. I tried it there. It was impossible to agree on something. But the 3 years we had spent together by that time helped us to agree on something. So same geophysical data. And it means, like, for example, land cover is a 30-meter resolved data set. If we have a lumped model set up, of course, those 30-meter gridded get somehow aggregated to basin scale, but they were not allowed to use any other land cover information. Most of the models also used exactly the same routing product, which basically takes care of the fact that everybody is using or modeling exactly the same watershed. But also the models that are distributed or semi-distributed need routing information. So everybody used exactly the same, except one model that sticked with the traditional native routing scheme in the model. We all also use the common set of Streamflow stations for calibration and validation. So that means Hong Ren actually went through thousands of stations and selected the ones that have enough data where the delineated area matches what ECC, for example, or Border Survey Canada is reporting. He looked manually at all of these hydrographs to look at there's something weird going on. We ended up with this common set of Streamflow stations that we shared then with everyone. So I wanted to highlight, this is all data stuff. That's what Hong Ren spent a lot of time on, supporting people, aggregating data for them, merging, extracting, whatever, bringing it to the same format. Hong Ren spent ages on this. But we also, the next point on the list is that we also used a common set of variables for model evaluation, because that was one of the most requests we got for GRIP-E was, you're looking at Streamflow, that's cool, but could you also look at other things, additional things, where other models might shine more that might not be as good for Streamflow. So we did that, and it was a real, it sounds so easy, but it was a real challenge to find a variable that the reference data set is not a problem to find, but to find a variable that all these 13 models actually output that you could compare was a challenge. So we ended up using evapotranspiration, surface soil moisture, and soil water, snow water equivalent. And we are using the same methods for comparison. So everybody had to send the model results to me, and I derived all the metrics and comparisons, no cheating whatsoever possible. The paper is actually published since last Friday and has All the detailed results can be found there. I will just give an overview of what we actually like, the highlights. The models, the 13 models for completeness are these. The first one is the machine learning model. They will always be in every plot, in every analysis, they will come in exactly that order. The first one, machine learning. Then we have those 7 locally calibrated models. And then we have the regionally calibrated models with the different people indicated on who set up which model. So how did we start? So of course we started with Streamflow. That's where we all feel very comfortable with. We calibrated first against Streamflow. Nobody actually knew about validation at that point. Like, people had heard like we might do a validation, but nobody knew the exact specifics. So it was very blind what we did in validation. So we had selected 141 Streamflow gauge stations from both the US and the Canadian side for calibration. And then Hongren and I and Bryan, we had found 71 stations that we wanted to use for validation, but that list never made it out of our small group. Nobody else knew those until everybody had submitted the calibration results. Then we revealed it, which ones are the other ones, so nobody could cheat. So the first step was obviously calibration for the time period we used for calibration. And then, as I said, blind validation. We revealed also the data for the forcing data for validation period after everybody had finished the calibration. Was a good timing because this data set we are using wasn't public by that time. I only had received the data for testing. So then we also did, as I said, spatial validation, which is we stick with the calibration period, but use the new set of stations. And then we do the hardest task is we move to stations we had never seen before, and also a time period we had never seen before, which is called spatio-temporal validation because space and time vary. So 4 different experiments. Let's look at the results for the first one. That's calibration. So most of my results will look like this. So let me just walk you quickly through the plot in general before we talk about the results itself. On the y-axis, you see listed the models, again, machine learning first, locally calibrated, regionally calibrated models. On the y-axis, you see the Streamflow gauge stations. It's 141. It doesn't really matter that you can't read them explicitly, just that you know they are there. We group them into the stations that fall in the Lake Superior watershed, Lake Huron, Lake Michigan, Lake Erie, Lake Ontario, and the Ottawa River. So that's like these 6 groups, these 6 regions I was talking about. And then every grid cell is colored according to what's the performance of this model at this station. So the more blue we see, the better. In all plots, blue means good, red means not as good. On the right-hand side here, you can see the median performance across all the stations for this model. Okay, let's talk about the elephant in the room. The machine learning model here achieved almost perfect scores for Streamflow performance, right? Like, it's like the KGE of 1 is perfect. They got 97% in KGE. Which was kind of like, we were still like, okay, we were not panicking yet, but it was quite overwhelming how much better the machine learning models were. But usually those results for machine learning models are not even reported because they could technically get like a 100% score everywhere if they would want to. What we also see is that the locally calibrated model on average are better than regionally calibrated models. That's also kind of like it's good for confirmation. It's kind of what you would expect because they are calibrated at exactly those locations. So it's like the upper limit of where you can go with those models. And then what was good to see that there is no station that is bad for all the models. So that's Hongren actually did a really good job looking manually at all the hydrographs, that they actually look okay. But we have some stations where, for example, regionally calibrated models don't seem to work. So in the paper, we go through every single station and try to find an explanation why they might not work at this location. let's go to the first validation experiment. So the only thing we changed, it's the same calibration locations, but it's a new time period. Still same location, but new time. So what we can see is everything drops, like all the performances drop. It's kind of like expected, but still the machine learning model is the best across all the models. It has the highest score by median, but and also if you look at it, it's just a blue row. So there are some models that are actually pretty close, like this one here, like the blended lumped model is actually not too far off. The locally calibrated models are all pretty good, actually. Like there's like the second best group. The regionally calibrated models are like lower in performance, but still they are modeling the entire region, not just like they don't cut out just like the regions they want to look at. They do the entire thing. So they might shine once we do spatial validation. But there's like models that are really good, like the Watt-Flood Raven is actually really good. SWAT Raven is also good. Some surprises, not too many. Some stations that just don't work anywhere for the regionally calibrated ones, but overall not too bad. Let's go to spatial validation. So we are changing to those 71 validation locations. That's where things became really interesting. And we go back to the calibration period. So at least like one thing we still know is the time period. But here it became apparent that the machine learning models are just knocking everything out of the park because they are so much better than even the second best hydrologic model. Like the gap is maintained. It was not just a huge gap in calibration where they got the 0.97 KGE. They are also maintaining that gap in validation, in spatial validation. It's a sight they have never seen before. So that was very surprising. And kind of like, oh my God. The regionally calibrated models are still pretty good, given that they have to come up with a parameter transfer approach. So since they don't know the basin, but they only calibrate at specific locations, and then you get a new location, you have to find out which parameter set to use for that new location. We used exactly the same donor basin mapping, it's called, for all those basins. They had exactly the same mapping. Everybody knew, okay, it's this new basin. I take the parameter set I have from calibration from that basin and use it here. So there's no variability in there, and it's a very simplistic approach. And that's certainly what you see here. There are some stations that just don't work for any of those models, but that might be that it's not because of the model, just because I came up with not the best donor basin for that specific location. But I wanted to keep things simple because if I would have tested different approaches, I would have needed to pick a model to test if it's working or not. And then implicitly, that model would have been like favored, right? Because I already tested with it. So I didn't want to do that before I just like chose the most simple one I could think of. The regionally calibrated models are actually like, there are ones that are really good, like Mesh SVS, Gem Hydro is actually pretty good and pretty close to some of the regionally calibrated models. There are some models that just didn't work, like what Mesh class. It's just like the performance in the median is just far away from everything else. So maybe there is some setup issue or something. But we still have one validation task to go, is when we also change now the calibration period by the validation period, and same picture. Machine learning model, it's way better than anything else, with only a couple of stations that don't work. So again, in the paper, we look at which are those stations and why might they be different. In this case, it was like the highly managed basins that didn't work that well. And again, the locally calibrated models are actually now way closer compared to the regionally calibrated ones, like on average. There are some that are really good, like the blended lumped model is really good, actually like the best out of the others. And then the regionally calibrated models, there is, for example, Watt-Flood is really good, Mesh SVS is really good. and some stations that just don't work anywhere. Again, it's all in the paper, which what are the reasons for that, but we identified that urban areas don't work that well. Agricultural regions in the US are really tough to model for the regional models and so on. So we find reasons for those stations in the paper. Okay, almost there. We are done with Streamflow. We are now doing model evaluation. So what I wanted to say in validation, the models were frozen, right? They were only calibrated and then they were never touched again. And that's exactly what we also do in model evaluation. We are just dumping additional model outputs, but don't touch the models itself anymore, just additional outputs. So as I said in the beginning, in the introduction, it was really difficult for me, at least, to find variables that are modeled by the most simplistic models and also, of course, the most complex models to agree on something that we could actually all compare with. The reference data sets we used here are coming from the GLIM data set. That's a 25 by 25 square kilometer resolved data set. They are daily. And we also wanted to use a gridded data set for SWE, just for the reason that I wanted data sets that are covering the entire domain. And I wanted to use exactly the same approaches for comparison. So if I would have picked station data sets, I would have needed to come up with other approaches on how to compare models with a gridded or like with a station data set. So I wanted to have everything gridded to make it easier at that point. Because still we can compare in different attempts. We could lump everything to basin scale again, as we do with Streamflow, basically. Like we would have just 212 basins where we compare AET or SWE with. But if we lump our outputs, of course, the models that are semi-distributed would suffer from that, because they are actually supposed to be good when we look at the grid scale, right? Like at a finer resolution. So we also picked a comparison method where the distributed models could shine, right? Where they resolve that variability. So we also compare grid cell wise, even the lumped models, they got transformed into gridded outputs, and then we can compare them there as well. And then there was a larger discussion going on, which metrics are we going to use to compare those, like reference data set with the model output. We tested a lot of them, we looked at them, and then we decided, let's just go with KGE. It basically was not too different from any other metric. So we used KGE for evapotranspiration and snow water equivalent. And for surface soil moisture, we had a real problem, because a lot of models actually don't model soil moisture. So they had provided a proxy for soil moisture. It's because they don't actually have like soil layers in their model. It's like there's an open bucket basically. So you cannot derive a percentage because there is no ending to that soil layer. So they are deriving proxies. And therefore we couldn't use at the actual values, the nominal values of soil moisture. So we are only comparing correlation. The correlation between the output and how it should like vary in time. So that's like the KGE, the correlation component of KGE. That's how I called it. So these are the metrics. And the results, again, we first looked at basin-wise. So the results actually look very similar to what we looked at Streamflow, because it's at each individual subbasin on the x-axis. Now we have 212 on the x-axis, the 141 from calibration, and also the 71 from validation. We just pulled them all together. And again, blue means good, red means not so good. So kind of like, for example, Lake Superior watershed looks pretty good all across all the basins. But we have some basins, for example, Lake Huron, there seems to be like a region that isn't working too well. But then there's Lake Michigan, works really good for regionally calibrated models. Locally, there's some locally calibrated that might suffer here and there. But maybe that's like the validation basins, you know, you don't know where these basins are located right now. You're just like, can see like a rough guess of like a rough picture of what's going on here. What we can see is Gem Hydro is really good, has a really high score on average. There's also Mesh SVS is pretty good, but we also have locally calibrated models like the blended Raven model is really close to the average performance of Gem Hydro, even though it's a locally calibrated model and it had suffered from all this spatial, like these regions where it was never calibrated or even set up for. So it was pretty surprising. But we said like, okay, it's lumped. These models, like the regionally, the distributed models might suffer from looking at lumped outputs. So let's look also at the gridded outputs where we can actually now see where models are not so good because we look at maps. So every colored grid cell you see here is basically the correlation. In this case, no, it was the KGE performance of the model at this grid cell versus the reference data set at this grid cell. So you're looking again at time series at this grid cell. So the color makes the correlation coefficient. Or the KGE in general. So we can see that Gem Hydro, for example, is suffering a little bit like south of Lake Huron and north of Lake Erie. So there is this corridor where it doesn't work that well, but we see that pattern for a lot of models. Like this corridor seems to be really difficult. It's lake effects, highly urbanized, a lot of agriculture. Like there's a lot of things going on that make it really difficult for a model to work there. So you can see, but really interesting what you can see here, especially for the data set, that's why I'm showing SWE here, is that there is differences between if you look at the basin-wise, this results, and these results, because for example, the ranking of Mesh SVS and Gem Hydro is flipped. So Gem Hydro is not as good as Mesh SVS anymore. It's like the median score decreased for like Gem Hydro is less, while for the basin-wise was exactly the opposite. It's just because the aggregation of a highly variable like SWE, AT is much more smoothed out, also Solmoisture is very much smoother. There it really matters. So it's one major outcome of the paper is if you have a variable that is highly variable, you want to compare, better look at grid cell, at like that resolves that variability when you look at it. There's differences in the outcomes, basically, if you're interested in that. Okay, so that was like my excursion to the evaluation variables. And now we are basically at the finish line. We had like no model had to be run anymore. All analyses were done. We had all outputs in the right formats whatsoever. But we wanted to know model, like we have these 13 or 12 models. What is the overall best model? Like when we combine all of them, we had now looked at the individual ones. So how does it incorporate, like get together? And for that, we did a multi-objective, multi-variable analysis that was like new to everyone and probably maybe also to the people here. So I want to walk you through the concept of what we did before I actually show you the results. So let me walk you through this here. So what we have is several objectives. We had Streamflow, we have AT, soil moisture, and SWE. We have 4 objectives that everybody had to provide outputs for. For simplicity, I only show 2. Let's assume we would have only had 2, Streamflow and AET. And we have 12 models. Each dot, it's 12 dots in total. We have 12 models and they have a score for Streamflow and a score for AET. So they are located somewhere in this space. And this here is, let's say, my model. So I'm interested in how my model is doing. What I can say about my model is that it's definitely better than these 3 models up here, because in both directions, it's better. This is where we want to go. Utopia is the place where we want to be. Because in direction to utopia, I'm better than all of these 3 models, right? But on the other hand, my model is definitely not as good as these 2, because I am in both directions, I'm worse than these 2. So how this is called in multi-objective is called that this model is dominated by these 2 models here. So now the interesting models in the set here are the models that are not dominated. You cannot say that any model is better than this model because you cannot find a dot in this rectangle to the bottom left. And there are several of them here. It's these 4 models where you cannot find anything in that rectangle. And this is called a Pareto front. So that's like a brief introduction to multi-objective calibration, because we want to see that Pareto front, because that's the models where we cannot decide which one is better than the other. They are equally good. One is always better in one objective than the other. So now what we did, we can do this plot for every single basin. We have 212 basins. We can find 212 Pareto fronts, like we are plotting this Pareto front for all the basins. And what we are doing, we are counting how often a model is part of that Pareto front, because it's like one of the good ones. So a model has a perfect score if it's 212 times on a Pareto front, like in every single basin, it's on the Pareto front. The worst score is 0% because it's always one of the gray ones here. That's the score we are looking at. 100% best, 0 not so good. We did that for all the models, all the basins. Best model overall is Gem Hydro. Gem Hydro was on 89% of those tests we did, 89% of the basins part of the Pareto front, so not dominated by anything else. The coloring here is a little bit different, like the blue ones are the ones that are regionally calibrated. The red ones are the locally calibrated models, just to separate them a little bit visually. There's another model, a locally calibrated model that is really good. It's HiMod 2 is part of the Pareto front 85% of the times for calibration basins and 82% of the times in the validation basin. And then there are some basins that are, some models that are clearly not as good. But we have some that are really good, like these 2, Mesh SVS, Gem Hydro, for the regionally calibrated ones, and locally, the HiMod 2 model. That's when we are taking into account all the 4 variables that we actually looked at. But I got interested in why. Why is Gem Hydro, why is HiMod 2 so good here? Because it never really excelled in the other variables. I was so surprised when I saw that. So I wanted to dig a little bit into why this is happening. So we took away AET from this evaluation. So we only have 3. It's Streamflow, soil moisture, and SWE. And we can see that there are some models that are significantly decreasing in being part of the Pareto front when you take away AET from them, which means in turn, the reason why they are on the Pareto front is because they are so good for AET. They are dominating so many models because they're so much better for AET simulations. So what you can learn from an analysis like this is HiMod 2 is really good for AET. We should look in this model how it's doing AET. Maybe we can learn something from it and improve our models by doing AET in our models as they do it in HiMod 2. So that's kind of like the analysis. We dig a little much deeper into this in the paper. We also take away all the other variables and look at this and the reasons for this and things like that. That's like that's the last section basically of the paper, bringing everything together. Okay. So I thought I'm done by this point, but no, I had to write the paper. We also wanted to come up with a website, there's so many results we have here, and not everything we can present in this paper, right? There's only this heat map plots, but you might have seen, you have not seen a single hydrograph by now, right? And that's what hydrologists usually are interested in. So that's basically what came after. It's we had to share all those data, the website, the paper writing. But I'm really happy the timing couldn't be any better because the paper got published on Friday. It's all done. We also published all the data sets we used here, but that's not entirely true. We are only sharing the data such that if you have a model that you would like to contribute to this model intercomparison, you get all the data you need for it. but we hold back the data for validation such that you would also need to do as blind validation. So it's the part of the data that everybody got in the first place. I have prepared all the other data as well. So as soon as somebody sends me all the calibrated Streamflow data sets, you get the second portion of the data as well. It's all described on further. It's a very extensive README file for the data set. And something I'm extremely proud of, we developed during the project, because people were just like, can you please prepare some plots for hydrographs? And I'm just like, I'm not going to prepare 3,000 plots. I'm too lazy for that. So I came up with a website where everybody could basically explore the results. And I just want to walk you through real quick. The data are on HydroHub. So you would go to hydrohub.org. We arrive at this website. There's different things there. One is model intercomparisons, and you would go to obviously GripGL. There's a little bit of introduction there, and then you can find those maps here, like one for Streamflow and then one map each for the additional variables, AET, soil moisture, snow water equivalent. So let's go to the Streamflow simulation map. Gives you some introductory words of what to do, what you can find here, but in the end, I hope you can see this. And so what you can see is basically all the dots for the watersheds. You can go over them, you can see the actual watershed, and you can click on them. If you double click on them, you can see which watershed it actually is, what's the drainage area. You can download all the results for that watershed, a shapefile, the routing, whatever we had prepared for this. But of course, you also see the hydrographs. So now the interesting thing is you have all the models that participated here in the right-hand corner. So you can see like I'm really interested how Gem Hydro is doing here. So now it's Gem Hydro with the observations, or how did the LSTM doing here? So the LSTM had a score of 0.984 in this basin. Gem Hydro of 0.22, but and then what you cannot do in a static plot, you can now of course zoom in to that one flood event you are most interested in, right? The other feature we have on the website is you have like things here in the top right, left corner, and one is coloring of the markers. So right now they are all white, very boring, but you have options on how to color them. So for example, you could color them according to the performance of the LSTM model. So everything blue because everything they are so good. Let's find a model that has a little bit more variability, maybe the blended Raver model. So you can find stations, the ones that were red in the heat map plot, you can now find where they actually are. You can look at the hydrograph, you can see what's going wrong here, like what do I need to improve in that model in getting it better there. But you can also color them so that you have the performance. You can also color like basin characteristics, like for example, what's the annual temperature in all those, in all those watersheds, like warmer in the south, colder in the north. You can also do the coolest feature, probably a little bit buried under all the overwhelming things you can find here, is the ranking of the models. So what this is doing is, let me just position it in the middle. The models you're selecting here, you can see, let me just get the LSTM away. The models that you're selecting here, you can see which model is actually the best at the location. So yellow location means Gem Hydro is the best model, the better model between these two, while at the pinkish dots, the blended model is better than Gem Hydro. So and you can do as many as you want. You can GeO4J, okay, it's a few locations GeO4J is actually good, but like SVS, or like you can just put other models in the pool and see where which model actually, like if your group provided two models, you can actually see where is which model better. So that's all like non-static things, exploration of the results that you will never, like we would never be able to put in a paper, right? Plus, if we are adding additional models to the intercomparison in the future, because we have provided now all the data, we cannot add them to the paper, right? But we could add them to the website, right? So that would be kind of the plan, that the website is the evolving part of it, while the paper is certainly like static snapshot of what we have right now. So let's go back to the presentation. I'm already almost done. I just put this also here. It's the summary of what I just explained. We see this as a living database. That's like the core idea here, right? And then just the main conclusions. I think I talked about all of this here, but just in the sake of time, I will leave this slide up here. And would be happy to answer any questions, or if Bryan wants to say any additional things that I might have forgotten. Yeah, I would just stop talking right now and just thank you for your attention. And I'm really looking forward to questions. Stop talking now.
I don't have anything to add, just that if anybody wasn't following the chat, all of the links that were in Julie's presentation to the paper, to the data, to the website for the project, they're all in the.
Awesome.
It's all
Thank
in
you,
the
Bryan. Awesome. Thanks, Bryan.
Thank you so much, both. It's been an incredible amount of work that you walked us through there, and the website is quite amazing. I did have a chance to play around with it and just locating the gauge where they're located and just seeing the color change reflect model performance is quite incredible.
Okay, cool. Yeah, that's quite straightforward once you have all the results. And it was really like, since we only had those static plots in our monthly meetings, it was really like when we looked at those heat maps, everybody was just like, I cannot read the gauge ID here. Which one is it? Where is it actually? Is it that station that is under the highway that is just like, you know, getting all the water from the highway? And that's why we don't have that in our model. That's why it's not working. Like, and with the website, it got everything got so much easier during our internal meetings during the project as well, that it was quite like a natural evolution of also which features did we want to have in the on the website. Everybody had just like, oh, I wish I could look at this in more detail. Yeah, so that's kind of how we came up with it. We would probably not have done it if we would have had like 3 models and 5 locations. I think then you can produce all those plots. But with this much, I think it was a good idea to come up with the website.
No, I think it's very, very useful. And I do want to open it up to questions to the audience members. Please feel free, if you're comfortable, to unmute and ask your question directly. You can even you can turn your camera on if you're comfortable, and if not, feel free to post your question in the chat as well. First, we just got a question from Ignacio. I hope I'm pronouncing the name correctly. He's asking, did you validate lake water levels?
No, we didn't. We didn't look at that at all, but it's a good idea. But we like the point is like that. Only like the regionally set up models would have like any estimate like for water levels. Like we wouldn't have had that for like a locally set up model, right? Because like for the water levels, you need to simulate every runoff basically that goes into the lakes, and also you have to simulate like the evaporation over the lakes, which most of the models didn't do. Like the locally, regionally calibrated models didn't do that for sure. So that's why we didn't touch that. But it would be definitely interesting to look at that.
Thanks, Julie. Thanks, Ignacio. Feel free to follow up as well if you had more questions on that.
Did that answer the question, Ignacio?
Yeah, he did say thanks in the chat box.
Oh, okay, perfect.
I think that means yes.
Yes.
But yeah,
I see you. Yeah, I see you nodding. Awesome. Thank you.
There is one more question from Nancy. Who do you think might be most interested in these results? So think governments, conservation authorities, etc. Who would be able to use this to see which models are best for them to use to make local decisions?
Probably, like, I mean, I think what we learned from this is also like that there's quite a diversity. There's probably not that one model that is good everywhere. but also like that it might be a combination, like there is some models that are really good like locally, but it really also depends on what you want to do with the model, right? Like even though a locally calibrated model might be like really the best for that one variable that you are most interested in, you might want to have a regional, like a setup for the entire domain and not only for one basin. So it really, I think it raises mostly like the awareness of that there is a lot of variability for some variables between different models, but also like that machine learning models, we cannot ignore them. I think that's also one of the things that we learned here, even though they haven't provided results for the additional variables because they would have needed to be trained on those variables to make estimates for them. It's possible. We cannot ignore them. Like if the task would have been just give us something for soil moisture, you can also slightly calibrate to it. They would have probably, there's just a recent publication came out where they did exactly the same model, but they trained a little bit for soil moisture and they had excellent scores for soil moisture and SWE and so on. So I think like it probably raises more awareness than like probably like use this model for whatever you want to do, right? It's more like there's different models that serve different purposes. And what variety of models we also had, right? Like this intercomparison was so complicated because there is no straightforward way to compare all those models or all those outputs. Like that was already like mind-blowing to me. There is no metric or approach how to compare gridded AET for a model that is semi-distributed and a model that is lumped. There is no common approach for this. So I think we tried to come up with like a framework. I think that's what we contribute here, a framework that if you have a new model, you cannot claim anymore saying like, my model is better than yours. You now have a benchmark where you have a specific set of inputs, you have a specific outline, what you do that with your model, and then you can compare with 12 models that did exactly the same, right? I think that's maybe, that's at least from my point of view, the main contribution here. Maybe less the nitty gritty, this station is better for gem hydro and not as good for watt flood. I think that's like, it's more like the bigger scope. Nancy, I hope you like that answer.
Yeah, Nancy, if you have follow-up questions too. So Nancy is part of our knowledge mobilization team at Global Water Futures. So she definitely works, I think, with a lot of she considers a lot of the user needs and some of our project design strategies, approaches, communications, outreach. Just really that big picture of how do we get users involved, how do we make what we do useful to our users directly, especially in decision making. So Nancy, if you have comments as well, feel free to unmute at any point.
Yeah.
And
Bryan, Bryan, I saw you nodding in between, but like, do you agree or do you have like something to add?
That was a good answer. I would say that more directly to Nancy that certainly the NDMNRF, who is responsible for flow forecasting in Ontario, knows, at least in Northern Ontario, they know about the results. They've looked at the paper. Conservation authorities, if they haven't yet, will certainly hit them up. I hope to invite them actually for a workshop to campus in the fall. And I would imagine we would redo this talk for them with an emphasis on looking at Ontario specific results. So yeah, thanks. Oh, there is another question up from Jonathan, it looks like.
Yeah, Jonathan, please go ahead.
Yeah, can you hear me?
Yep, loud and clear.
Okay. Thank you, Julia and Bryan, for this massive job. I mean, it's kind of impressive. The experiments are very clear. So I am curious about, you start comparing the Streamflow, but then you use other variables, yeah, for comparing. These other variables are, do you believe there are more uncertainty than the Streamflow? I mean, I try to understand which is the variable are more true in order to compare the the best performance of the models?
Yeah, that's an excellent question, actually. Like we calibrated only Streamflow, right? That's why we started with Streamflow, and then we only took like model outputs after. Like for a calibrated model setup, we also dumped basically what the model had simulated for AET and so on, right? And we use like as reference data sets. I wanted to use gridded data sets for some reasons, because like they are way more out there. But of course, those reference data sets, those gridded outputs, or those gridded reference data sets are not ground truth, right? They are modeled themselves. It was probably primarily like a station data set. Somebody interpolated, was running a model like an AET model to fill the gaps and things. So that's something we really need to keep in mind, that those reference data sets are modeled themselves. But we were aware of that question might come, especially working with Canadians who know about ground truth SWE measurements, right? Especially there was one person even in the project who just had published a Canadian SWE station data set. So what we did is we compared that station data set with the gridded SWE reference data set that we had used to compare the models to. And that's part of the paper. Like it's in the supplements, but we have a comparison of the station data with that reference data set. I have that in the supplements. Here. So we compared the stations that were falling in our study domain, and it's a Canadian SWE data set. So there is nothing on the US side. We initially had thought of using that data set, but then I thought like, no, I want to see how we are doing in the US as well. So that's why we did it the other way around. So we compared how they are matching, like from the CanSWE, like the ground truth with the reference data set, and that's basically how they compare. There is like 57% of the stations have a KGE above 0.65, and like 83% of the station have a KGE they match with like a pretty good KGE score. So there are some stations that don't work too well, like those down here, the red ones basically. But that's actually like the person who did that comparison is the person who did put together that station data set. And he said, I'm actually not so sure if the ground truth data set is correct at those locations. We might have a problem with a unit conversion there, because it looked like how it developed over time, like the time series looked pretty similar. It was just shifted. So he was not so sure if actually the reference data set in that case is the right one and the ground truth is the wrong one. So we were pretty happy with the graded data set. So I guess there is more uncertainty in those, but you have also a lot of uncertainty in Streamflow data sets, right? So I think it's probably like not too far off. Long answer. But you know, the short conclusion is it's probably the same, like similar uncertainties as in every data set. Stop sharing here.
Thanks, Julie. So I am conscious of time here because we still have one more presenter. Mohamed will be telling us a little bit more about what the Nelson Model Intercomparison team has been up to. Thank you so much, Juliane, Bryan. And for the audience here, please feel free to still post your questions. We'll try to get them at the end. And if we don't get them at the presentation, we'll follow up individually as well. All right, Mohamed, you're on.
Thanks, Leila. Thanks, everyone, for your attention. Before I start, I just would like to start with a land acknowledgement. It's always a great honor and a pleasure to live, work, and present from the traditional Treaty 7 territory in southern Alberta, the homeland of the Métis Nation, We always pay our respect to the First Nations and the Métis ancestors of this place. And second, I just would like to acknowledge the effort, support, and contribution from our collaborators. None of this work would have been possible without their contribution and support. So a big thank you. A bit of introduction in here. As you all know, hydrologic models have been continuously developed and used to predict the various components of the hydrologic cycle. And also they have been used to predict various risks to the communities, such as floods and droughts. Due to the continuous development of these hydrologic models, there are currently so many approaches to represent the same hydrologic process. And therefore, intercomparison projects and studies play a major role in here in testing those different hydrologic models and identify their limitations. As you saw from the previous presentation for the GREG-GL project, we can see that most of the intercomparison studies in Canada have been focused on the Great Lakes area. Recently, the GREG-GL, and before that, so many studies that focus on individual lakes out of the Great Lakes area. And so far, there is no intercomparison study that has been done to central or western basins in Canada. And this has been mainly due to the very challenging hydrology of that region. It's known that region is very complex, very challenging, wherein typically most of the traditional models fail in that region. And therefore, this region will be a good test case, and the area will benefit also from intercomparison studies, since they can shed more light on the complexity of that region and also can highlight areas of model limitations or model structural problems. Therefore, our objective here for this study is to intercompare the performance of multiple models over a major river basin in Western Canada, and we have selected the Nelson-Churchill River Basin for this study or this project because of its importance and its complex hydrology. We have compared the performance of the different models with regard to the streamflow simulation as well as other hydrologic variables. And also by the end of the study, we were able to identify a set of models that have accurate streamflow simulation relatively over the entire Nelson-Churchill River Basin, and more importantly, highlight areas where these models need future model structural improvements and their limitations. So this slide here shows a bit of an overview of the Nelson MiP project outline. Basically, the project has been divided into 4 phases, phase 0 up to phase 3. And this figure here on the right-hand side shows the timeline. Basically, phase 0, the main idea behind phase 0 is to get the models to be built and set up over the Nelson-Churchill River Basin and just run the models for streamflow only without any calibration. So the initial parameter sets will be provided or decided based by the different modeling teams. For phase 1, we just used the models that have been developed for phase 0 and calibrated them for the unregulated head watersheds within the Nelson-Churchill River Basin. But we compared the flows and other hydrologic variables. Again, phase 1 and phase 2, they only focused on the unregulated head watersheds within the Nelson-Churchill River Basin. But for phase 2, we take it a bit further and expand our test case to include the entire Nelson-Churchill River Basin, to include both unregulated and regulated watersheds. And for that phase, we will compare the flow, other hydrologic variables, as well as the regulations, like water levels within the different lakes or reservoirs, if possible. And the last phase of the project will focus on assessing the impacts of climate change using the models developed in phase 1 and phase 2, if possible. So far, phase 0 and phase 1 are done for this project. We have started receiving results for phase 2, but still these results are being post-processed and not yet ready for presentation. And this presentation will only focus on the phase 0 and phase 1 of the project. Just a bit of overview about the Nelson-Churchill River Basin. As you can see, this map here shows an outline of the Nelson-Churchill River Basin in Western Canada, where it shows the outline of the basin, the hydrologic features like the rivers, as well as the numerous lake systems within that region. And more importantly, this gray area shows the non-contributing area or the unaffected area. So the basin in total has an area of more than 1.4 million kilometers square, and more than of 0.33 million kilometers square is considered as ineffective. And by that we mean this area of the basin doesn't contribute flow to the outlet for rainfall or snowmelt events with smaller magnitudes. The Nelson-Churchill River Basin is divided into 7 major subbasins: the Saskatchewan River Basin, Assiniboine River Basin, Red River, and Winnipeg River, Lake Winnipeg, and the Lower Nelson River, as well as the Churchill River. So these 6 subbasins form the Nelson River Basin, and this is the Churchill River Basin. Generally, the flow is going from the west side to the east side, and for these basins in the southern area, it goes from south to north. Also, this basin has so many ecozones, which adds further to the complexity of the basin. The basin, as you saw from the general overview map from the previous slide, it includes major areas of the North American prairie region, which is dominated by numerous land depressions, wherein the fill and spill mechanism is dominating the runoff production. It also includes some areas from the Canadian Rocky region, wherein hill slope and mountain hydrology is dominant. It also includes part of boreal shield and boreal plain, wherein the wetland complexity and dynamics is dominant. The basin itself has numerous managed and unmanaged lake systems, as well as permafrost, and all of these features makes it very challenging to model this basin. So in total, we have 8 models that are running for this project, and we're part of this project. We have the HYPE model from the University of Calgary, the blended Raven model from the University of Waterloo, and these 2 models are running the full domain. However, the HYPE model is actually running all the Nelson-Churchill River Basin, whereas the blended Raven model is missing a couple of gauges, but we consider it as being a model that runs on the full domain. We have also the Watt Flood model from the Manitoba Hydro team, but this model is running on a subset from the Nelson-Churchill River Basin. It's running on a subset of the Churchill River, Lower Nelson River, and the Winnipeg River. And we have also other models that are running on either the full major river basin, so a subset of the major river basin, or an entire major river basin. And that has been mainly due to modelers' interest and existing modeling domain of that area. We have also the VIC model from the University of Northern British Columbia, which is running on the entire Lower Nelson River Basin, and the HIC-HMS, which is running on the entire Red River subbasin. And lastly, we have these 3 models, the SWAT GIW and 2 versions of the Raven model. And these 3 models are considered as prairie models. And by that, I mean that these 3 models are the only models that have a dedicated component to simulate the fill and spill mechanism of the prairie land complex. The SWAT GIW from Water Security Agency is running on a subset of the Assiniboine River Basin, and the 2 versions of the model is only running on 1 gauge stations out of the Saskatchewan River Basin. In order to make the comparison consistent between the different models and to make sure that the different models are built using the same models, we have used a standardized set of meteorological and physiographic information, very similar to what has been done in the GRID project. We're using the RDRS product for the meteorological forcing, which is available from 2000 up to 2017. We have used the Merit Hydro DEM and NALCMS for land cover, and GSDE for the soil type of soil classification. We made sure that all the models that are participating in this study are using the same set of input data sets to make sure the model setting up process is very consistent throughout the modeling domain. The next step was to identify a set of gauge stations for phase 0 and phase 1. This basin is very challenging. It can be considered relatively flat, and therefore the identification of different gauging stations is very challenging. Therefore, we had set a criteria to make sure that we eliminate any problems that may come from the watershed delineation or from delineating a very small basins. So any basin that has an area of more than 200 kilometers square and it's considered as unregulated watershed or a head watershed, and it has enough flows record, we have used that for phase 0 and phase 1 of the project. This resulted in 132 gauge stations across the Nelson-Churchill River Basin, which are plotted in here. You can see that the different dots represent the different gauge stations, and each gauge station is colored, and the color is based on their reported drainage area. The second thing, we have set the simulation period to a period that has both flow observations as well as meteorological forcing data available. And for that, our simulation period is set from year 2000 up to 2017. The first year was considered as the spin-up period, and then the year 2001 up to 2011 is the calibration period, and from 2012 up to 2017 is the validation period. We have applied this criteria to all 132 gauge stations, and therefore there was no blind or special validation. We didn't follow the same exact approach that has been done for the GridGL. All the gauge stations have been calibrated and validated. We have used the median KGE as the objective function for model calibration, and that median KGE is only calculated for the simulated gauge stations, because the different models have been tested or have been built for different areas of the Nelson-Churchill River Basin. And we have also used the Klingopta efficiency, or KGE, for streamflow evaluation. We have also included two other hydrologic variables. The first one is the actual evapotranspiration, and we have used the actual evapotranspiration from the GLEAN product as the benchmark data. This data is available from 2003 up to 2017 at 0.25 degree grid for the entire globe. However, as Julie mentioned, there is a problem in comparing two data sets, the benchmark data and the model simulation, when they have totally different resolution. So we had to come up with a way to aggregate the GLEAN benchmark data and the AAT simulations by the different models. And our approach here is a bit different from the GridGL approach. We had to aggregate everything to a daily time scale in terms of the temporal scale. And in terms of the spatial scale, we had to aggregate everything to the discretization scale of the model. And what do we mean by that? We mean if we have a lumped model, then everything is aggregated to the watershed scale, because we know lumped model cannot produce spatially variable hydrologic variables. And therefore, if we aggregate everything into grids, they will have the same exact value for the current time step or for the same time step. We have also aggregated things to the sub-watershed or grid level if we have semi-distributed model. Therefore, we have made all that comparison just to avoid disadvantaging certain lumped models. For the AAT, we have used the Pearson correlation coefficient to measure the goodness of fit between the benchmark data and the observations. For the second hydrologic variable, we have used the SWE from the Canadian Historical Snow Water Equivalent Dataset, the CanSWE. And this dataset is actual ground point observations, as you can see from this map in here. The CanSWE data is available from 1928 up to 2020. And again, we had the same problem. CanSWE is point observations where the model outputs are either watershed scale or subbasin or grid scale. And therefore, we had to aggregate everything to a daily scale as well as discretization scale of the model. And for the SWE, we have used the root mean squared error as a goodness of fit measurement between the observations and the simulated. So in terms of results, the figure you see here on the right-hand side shows the distribution of KGE for the full simulation period with no calibration for the different models. So each faucet or each panel shows a different model. And these dots represent the gauge stations, and the coloring represent the KGE. I've also included a box plot for the KGE distribution for the simulated gauge stations in the lower left corner in here, as well as the median KGE across the simulated gauge stations. As you can see, most of the models, they have had unsatisfactory performance, median KGE less than 0.4, which is not a surprise. We know that these models were just built and the initial parameter set were even supplied to the models using either random values or any predefined values from any other watershed that has been used before. And therefore, it's not surprising that the models didn't show unacceptable performance. However, what's worth mentioning here that the HEC-HMS model and the watt flood model, they showed reasonably good performance or acceptable performance for the area that they have tested. I just forgot to mention that these gray dots that you see in here represent the missed gauges by the different models. So for watt flood and HEC-HMS, they missed pretty much most of the gauge stations, but they only were able to simulate some of the gauge stations. However, they showed acceptable performance when tested without calibration. And this also wasn't a surprise, since the modeling team that they used these different models have been building the same models for the same area over many years. and they have good knowledge of the area. Therefore, they have used their prior knowledge in supplying the initial parameter sets for the model to run, and therefore their models showed some acceptable performance. When we look at the results of phase 1 for the calibration period, we can see here that the blended Raven model showed the best performance, given that it has been applied for almost all the gauge stations across the Nelson-Churchill River Basin. It has a median KGE of 0.79, which is quite interesting. It has some problems in simulating some of prairie watersheds, as you can see in that area here, but overall it showed a good performance. Watt flood and HMS again showed good performance, but they have been tested on a limited number of gauge stations. Other models like the VIC model and the 3 prairie models, they have more or less showed good performance in terms of, or acceptable performance in terms of median KGE. If we go back here to the blended Raven model, we can see most of the gauge stations have really good performance. Even if we look at the distribution of KGE, we can see a very narrow range of the KGE distribution. For the HYPE model showed reasonable performance in terms of median KGE, but a wider range of KGE when we look at the box plot. HYPE showed good performance outside the prairie region, but it had very major discrepancies in simulating the flows within the prairie region. This is not surprising since the HYPE model doesn't have any component to simulate the fill and spill mechanism, which is a dominant process in the prairies. If we look at the validation results for the different models, we can see that there is a reduction in the median KGE across the different models. Relatively, Watt flood and HMS, more or less, they have the same performance. HYPE had more or less the same performance. The performance of median KGE for the blended Raven model reduced. But what's worth mentioning here is that the prairie gauges, or gauges that are located within the prairie region, that region that's highlighted in here, it was very challenging to be simulated by the blended Raven model. Even though the model showed good performance in simulating these gauge stations within the calibration period, in the validation period, the model wasn't able to preserve the same good performance, and the model showed great discrepancies. The same thing can be applied to HYPE. HYPE wasn't able to simulate those gauge stations during calibration or validation period. Again, for the 3 prairie models, they were unable to simulate the prairie stream flow for these gauge stations, even though these models have been built to simulate only 1 gauge station or 2 gauge stations, such as the SWAT GIW, but none of them showed acceptable performance. And this highlights an important problem in current models and their limited structural and their limited structure. Most of these models do not have a component to simulate the fill and spill mechanism, and therefore they were unable to simulate prairie stream flow. Even though the models that have prairie component, it seems that this prairie component is not adequate and it's not proper and cannot simulate the complexities quite well. To make the comparison even easier to look at things, we have aggregated everything for the calibration and the validation period, but with regard to ecozone. Because we know different ecozones, they exhibit the same dominant processes. As you can see, most of the models, they have relatively good performance. If we just set 0.4 as our threshold for the different ecozones and different models, you can see that the different models had median KGE, or most of the box plot that you've shown here for the KGE distribution is above that threshold. But if we look at the prairies, we can see that for the HYPE model, during both calibration and validation period, it had unacceptable performance and a wide range of KGE distribution. For the blended Raven model, even though it had good scores for other ecozones in the prairies, it has lower KGE score when compared to other ecozones and a wider range of KGE. The same thing can be noticed for the other 3 prairie models and for pretty much other models. The only exception here being the HMS model, and that has been mainly due to the fact that the gauges that HMS model is simulating are at the very downstream end of the prairie region, wherein the fill and spill process is not as dominant as those other basins in the upstream of the prairie region. Another ecozone that was a bit of a challenge in here is the Hudson Plain. You can see that the HYPE model showed smaller KGE or lower KGE performance compared to other ecozones. The same thing can be noticed for the blended-driven model Earth and for the BIC model. And this can be due to the fact that the Hudson Plain area is also dominated by numerous land depressions and numerous unmanaged lake systems, which also control the runoff production by a fill and spill mechanism. So more or less, it has the same fill and spill mechanism as the prairies. And on top of that, it has the permafrost complexities, which is also adds to the hydrologic complexity of that region. If we look at the actual evapotranspiration simulation by the different models, this figure here shows how the different models perform in terms of the Pearson correlation coefficient. Again, and what's worth mentioning here, that we were unable to include the watt flood model in that comparison because watt flood model only produces the AAT simulation in a binary file format. And we were unable to know the format of this binary file, and therefore we were unable to read it. The only program that can read that file is the Green Canoe software. And so far, it's very complex to extract a time series from the different grid cells that have been used by the watt flood model. Again, the main purpose behind this is not to compare how the different models compare to each other, but to highlight areas where different models are struggling. And therefore, the comparison scale between the different models is a bit different. Overall, the different models have relatively good score in terms of simulating the actual evapotranspiration when you look at the median Pearson correlation coefficient. Again, this figure is very similar to the flow distribution. It has pretty much everything but for Pearson correlation coefficient. And instead of gauge station, it's now for subbasins or a major, not major, or a watershed. Relatively, the median KGE is pretty much acceptable, except for the blended-driven model here, showed unacceptable performance in simulating the evaporated fluxes. And if we look at the prairie area here for the blended-driven model, we can see major discrepancies in simulating that prairie region. When we look further into that, we found out that the models are overestimating evaporated fluxes. By default, the blended-driven model, it doesn't have any component to simulate the fill and spill and the abstraction that the different land depressions are doing to reduce the amount of runoff that's being translated into stream flow. And therefore, through the calibration process, the model has tried to overestimate evaporated fluxes to get rid of more water, since it doesn't have a component to simulate the abstraction that these land depressions have had on the stream flow production process. When we look at snow water equivalent simulation, we can see that we were only been able to incorporate only 4 models. The rest of the models were not included because they either do not have CanSWE observation within the simulated basins that they have simulated, or we were unable to retrieve SWE amounts out of the model, such as the SWAT model. Again, the scale is very different here between the different models, but this is not our concern. Our concern is to look at where the different models fail. Overall, the watt flood model showed relatively good performance in simulating SWE. It's expressed here as points where we are unable to get the grid information for the watt flood model, so we have used the point observations. For other models, they showed acceptable to unacceptable performance. But what's worth mentioning here is that over the Canadian Rocky area in both the blended-driven model and the HYPE model, there are significant discrepancies in estimating SWE, and this is expected due to the very challenging dynamics of the different snow on ground in here. Blowing snow plays an important role in that area, and therefore most of these models do not have a dedicated component to simulate the blowing snow and the heterogeneity in the landscape. We can see also that there are some discrepancies across the prairie region, which is also dominated by blowing snow and sublimation, which cannot be also, or it's not appropriately simulated in different models. The other thing that's worth mentioning here is that when we aggregate things into a larger scale, such as this watershed in here, things got bad. And this is expected, again, since we are aggregating or eliminating most of the heterogeneity that's known for the snow cover and averaging everything into a larger scale. So as you have seen, this project has so many challenging. The first of all is the basin itself. The basin is very complex, it's very challenging. It's dominated by various ecozones, and with each and different one of those ecozones have its own unique dominant process. The basin can be considered relatively flat. It has so many internally drained basins, which makes it very challenging to estimate the contributing and non-contributing area by the different models, and made it difficult for the delineation process. Again, this kind of projects require considerable time and effort in building models and post-processing the outputs. And most of the participating team, they didn't have time and resources to invest in this model, and therefore we have been limited to only 2 models that run the full domain, and the rest of the models only run to a subset of the modeling domain based on their interest. So just to wrap this up, again, Nelson-Churchill River Basin is very challenging, especially in the prairies. And the 2 main take-home messages out of this presentation is that, number 1, the models need significant improvements in terms of simulating prairie dynamics, because the models are either missing or not adequately representing the complexities of the prairies, which lead to unsuccessful simulation of prairie stream flow. Again, the models need significant improvement in terms of snow dynamics to make sure that the models are simulating the blowing snow effects as well as the accurate amounts of sublimated snow throughout the winter. The second take-home message is that some models are giving the right answer for the wrong reason. Some models are giving good stream flow simulation for prairie watersheds during the calibration period, and they failed in the validation period. But their good performance during the calibration period was found out to be due to overestimation of actual evapotranspiration. The last 2 things that this study will be very useful, since it has highlighted areas of model structural limitations and can highlight which models are appropriate to be used to accurately simulate the Nelson-Churchill River Basin stream flow. Again, we have seen from this presentation that the blended Raven model showed a good performance for almost all the gauges outside the prairie region, as well as the watt flood model and relatively the height model. These kind of models can be used by practitioners to be able to simulate stream flow within the Nelson-Churchill River Basin, and this would be allow them to do better job in managing water resources and in better allocation of water in that basin. And lastly, efforts are currently being made to test the same models and expand their area of application to regulated gauge stations of Nelson-Churchill River Basin. But again, these results are still in the post-processing step. So thank you so much for your attention. These are my contact information. Please reach out after this presentation if you have any question or if you are interested to learn more about the project. Thank you so much.
Thank you so much, Mohamed. We do have a couple minutes. I'm gonna, first of all, just open it to the audience to see if there's any questions.
Sure.
I have a question if nobody else does. Can't go without any questions, Mohamed.
Yeah, sure.
Great talk. Obviously, I'm part of the project, so I know most of what's going on. I was wondering, you have a nice map of non-contributing areas, right?
Yeah.
Do you have a map of non-contributing areas on a gauge by gauge basis? For every gauge, could you claim, okay,
yes,
59% of the drainage area is not actually draining to this gauge?
Yes, I can do that, and this information is available on the Water Survey of Canada product. So without any maps or anything, the Water Survey of Canada product, it has the total drainage area and the effective drainage area.
Oh, so the Water Survey of Canada has already estimated that.
Yes.
Okay, very good. I didn't. It's one of those pieces of information on this Water Survey site that I've always ignored because we typically don't work in the prairie. So
yes,
effective drainage area.
But again, I don't want to disencourage you, but the fact that this is not very much helpful. This is, as you know, the contributing area is dynamic. It's not fixed. It changes from year to year and from event to event. So this area that has been reported by Water Survey of Canada, and even for that map, it only corresponds to flows with return period of 2 years or smaller. Anything other than that, this won't be valid.
Okay, cool. Okay, thanks.
Yeah.
Thanks, Bryan. Thanks, Mohamed. I had a quick question.
Sure.
So one of the models you showed, I think it's a Water Security Agency, the prairie-based models. Is that, am I correct to assume the WSA stands for Water Security
Yes.
Agency model?
Yes.
Have you had a chance to hear their reflections? Do you know why some of those models are performing the least?
Yes, I can tell you why that's happening. Currently, most of these models, they are only simulating like the fill and spill mechanism in terms of a lake by lake, or they are only simulating everything as a lumped lake. These approaches are fine and they are good, but they are missing a very important phenomenon in the prairie, which is the hysteresis. These models, these are very good if you are modeling a number of lakes or a number of land depressions within the basin. But as you know, a typical prairie basin has thousands and thousands of these land depressions. And therefore, if you try to model these as individual buckets or individual storage units, you may not be able to simulate the actual hysteresis that comes with these land depressions. As far as I know, most of these models, they don't replicate the hysteretic relationship between the water storage and the contributing area in that basin, and therefore they fail. We have shown that for models that use the probability distribution, such as the Raven hyper model. It wasn't able to capture the hysteretic relationship, and therefore it failed in other watersheds. But I'm very sure that it will be the same case for the Raven hyper model as for the SWAT GLW model, which is for water security regions.
Yeah, I remember we had a chat about just how complex this region is, and it was quite fascinating. Thank you, Mohamed.
Sure.
We're right at the 10:30, or where I am, it's the 10:30 mark. If anybody else doesn't have any questions, I think we're good to wrap up. And feel free to reach out to any of the presenters or to me, and I'll direct your questions forward to them. Thank you so much for joining. Thank you so much for presenting. And we'll send you a link to the recording as well as a link to the feedback survey after the presentation. Thanks so much, Julie, Bryan, Mohamed. Really appreciate this.
Thanks so much for the opportunity. It was great.
Pleasure.